Yeah, hi. All right, so I suppose we can start this by small steps, right? While others will be connected as well, and we'll come to the class. Okay, so what do we remember from previous week? What did we do? What did we reach? What did we manage to do? Who can summarize a bit our previous week?
So
Yeah.
we talked about binary search and how to search the trees.
Uh-huh. Yes, that's good. What else did we do?
Of course, we did some programs.
hmm And we started one of projects which we tried to fulfill, right? What was that? Some kind of board, right? What kind of board? Yes. Okay. Well, we even talked about the hierarchy of classes, right? So inheritance, how it was implemented, right? Okay. Um, what else? We tried to implement the inheritance in chessboard as well for figures, isn't it? And what we reached? We reached that during making the inheritance stuff, we can reach some default values for the figure. If the figure is kind of the empty figure, right? It's just a chess item. And we literally can assign some values specifically for different class elements, right? Was it? Like we had symbols for figures, right? And then we try to use the console for coloring that. So we literally somehow interestingly show the chessboard, right? With figures on it. Okay, so the last thing we were talking about the trees, how to implement them, and what we literally have to. Well, what I would like to ask you guys. Well, let's suppose we have the array, and let's suppose we have a tree, because I assume that you have all of your codes, right? So it's not like you erased them. So the question is how we can be sure that searching, um, no, literally, let's call it differently. Um, what makes a difference or the penalty for using an array rather than using the tree or searching the values? Right? So what makes the penalty? Complicated questions from the morning, right? Okay, so how can you say, how could you prove that if we would like to have two approaches, one method is array and searching for data in the array using whatever methods you like, and the second one would be the tree. How can you ensure us that using trees faster? if you have just a raw data.
Depends how much data is it.
I would say it's equally depends. If let's say if you have millions of elements, right, you will have approximately the same impact on both of the methods. But another thing is how we analyze those methods. Think about the worst case scenarios and the best case scenarios. Yes, but how can you prove that? Question for everyone, by the way. Okay. Previously, before most of you came here, I asked those few students who were here, do you remember those certain algorithms we had here? We tried to use them in the C++ course, right? So how familiar you became with them? Okay, what was this? What was the certain algorithm? What's the purpose for that algorithm? Who can tell me? Maybe to sort? Yes or no? To sort data, right? Okay, how do we use those data afterwards? What's the reason for the sorting? Because we can search for elements without any problem, just going through the array. So why do we sort them?
So it will be in some kind of order, no?
Yes, why?
So that's why we use sorting. So
No. Okay, why do we need that order? What do we do with that order?
I guess make it easier to use those numbers.
What does it mean easier? Give me a description of easier.
Not that difficult.
Yeah, thank you. In IT, that fits well. When we program actions. So in case of the actions computer does by our codes, right? What does it mean easier? Maybe it's yes from your side.
Maybe easier to process the data.
Data is data.
Faster.
Yes, exactly. Faster. Why? And how do we get that faster? Previously you said one correct thing, one correct name of the method. Which would really fit as the answer here. the binary search. Yes? Okay, what was the binary search?
Search for exact numbers.
Okay, yes, but how the binary search? What was the method of the binary search? I understand the morning questions, yes, they're tough. I hope that's not a beer, right? Okay, great. Okay. But anyways, guys, seriously, the binary search, how that works? Why is it called binary search? Okay, but guys, it's not really cool because it means that you don't remember materials which we had during semester, right? Not cool, right? Yeah. Okay. So here we have a kind of overlapping stuff between the matrix method and the tree method. Okay. Why do we really struck those arrays? Well, for example, let's maybe take I don't know. All of them are kind of same, but let's maybe take one of these examples. And I will just scroll that a bit to have the array on the screen. Okay. No. Well, for example, like this. Okay, so here we have the array which is sorted, right? Okay. As you understand, guys, we can have such big array or much bigger, like millions of records, which is fine. So the question is, how well? Okay, we sorted that. We spent the time. It's a really big penalty, by the way, to sort the array. It's easier, it's faster to construct the tree than making the sorting algorithm. So what do we have here? We have 7 elements, and we would like to look for example, a value of, I don't know. Let's suppose 45. Okay, some of you would say, well, here we have, right? But let's say it's not us, but it's the computer, which is about to search that. So we have the sorted array. So what is the first step of the binary search? Badly. We look for the mid element. So we take the mid element, 23, and we compare that to the element we're looking for, to 45. What can you say about 23 regarding to the 45? It's less, right? So, which means that we have to look in the right side of the array. So for the right side of the array, we have to pick the mid element, 35. What can you say about 35 regarding to 45? It's less. So we have to look on the right side. So we have 45. Oh, okay, that works well. So it's exactly what we are looking for. And so literally, how many steps did we use? One, two, one comparison, two comparison, three comparison. So 6 operations literally. Why do I call that as the 6 operations? Because literally such search happens recursively. So it means we are copying all the data. in the memory. So that's we can say, okay, it will be additional operations. So that's the idea. Does it make sense? So exactly, that's why to apply such method, we use all of those certain algorithms. Okay, what was the difference between those certain algorithms? Who can tell me? We have tons of them. In the list, which we had here on the C++ classes, guys, 1, 2, 3, 4, 5, 6, 7 methods. What's the well? How they're different? Okay, technique is different. Okay, what else? Yes, amount of operations, literally. Okay, one of best methods here is the quick sort. Some people call that as horse method. Okay. By the way, there was a video with a folk group who literally implemented that in a way of dance. But I suppose you remember this. Maybe. Okay, we're not gonna to go through at this moment, but again, this method literally have a really small amount of penalty for that. Okay, yeah, so literally exactly that amount of operations. By the way, what happens when we search for data in a tree? Even if tree is constructed from unsorted data, we a priori spend less time for searching, right, than in the array which was not sorted, right? Yes, it is. We have seen that. So if the array would be sorted, well, that would be easier. Well, we would construct the tree within which we would literally, well, for sorted arrays, literally, it's more beneficial to start constructing the tree from the middle point. But again, it's kind of exceptional case because if we sorted the array, we already can apply the binary search. We're good so far, right? So as you understand, guys, just a bit kind of trying to go to materials, right? Needed sometimes. Okay, so yeah, so let's go forward. Well, it might happen that I wouldn't be kind of asking a lot from you maybe about the trees because because literally we made algorithms, and I suppose that most of you tried that, really tried on your computers. So we are going forward, but a type of the tree will be used at this time as well. So data compression. Some of you might have already looked on this code. Here I had some code samples, but I wrote them in Python, so maybe it will be a good helping hand for you to construct those algorithms in Java. I could do that in Java, but what's the point, right? Because you have to become more and more educated and more practically fulfilled in all this. Okay, data compression. What do you know about data compression, guys? What is the data compression? Who can describe me? Where daily we have the data compression?
Можно я скажу пару слов?
Да, пожалуйста.
Может быть, там как все.
Да, совершенно правильно, конечно, да. Ну, молодец, все верно. Умница. Кстати, мы будем рассматривать один из методов, который используется в 7-zip. So we'll be analyzing one of methods which is used in 7-zip. for a long time already. So data compression literally is used in most of the cases on our computers. So it's used for audio, it's used for video, it's used for pictures as well. It's used even for, as you mentioned, chips like a ZIP, RAR, 7Z, and so on and so on. Literally, there are a lot of methods which are different by the basic algorithm that's applied for different types of compression. So they could be the temporal compression, spatial compression, spectral compression, psychovisual exploit compression. Well, we're not talking about the last one, although it's a really interesting topic. I would say really interesting. But it's unfortunately far away from our main course, right? So, very interesting thing is that when we look for when we are looking, let's say a movie, right? Do we understand that the movie has some frames per seconds, right? Okay, and how those frames per seconds are organized? Well, we can think that we have full frames saved on the computers, right? But actually, it's not really so. We have only differences between the first frame and the next one saved. And we see the first frame plus an influence from the second frame, a difference between the first and the second. And that makes the second frame saved on the computer. That literally makes an optimization. And the same approach, and this is the simplest approach, is used in every type of compressions. Regarding two main aspects of compressions, there are two ways how to compress data. Well, we can compress data restoring the original information, like when we use archivers like 7zip or WinRAR or whatever. And we have the Lucy compression. The Lucy compression is used for the cases when it's impossible to restore original information. Examples: JPG image, MP4, AV. What else? MP3. What else? Blu-ray. Yeah, as well. Yeah, literally, it's impossible to restore data. But at the same time, we have pretty enough level of the quality still. Yeah. Um, so yeah. So since it was since I said that such things are used everywhere, well, images, sounds, movies, and so on and so on. What allows us? What makes it possible to make such conversions, compressions? Well, the codec packs. Well, what kind of codec packs do we know? Well, most likely, when you install a new operating system on your computer, you're looking for the codec packs, right? And most likely, what you do, you go for Google, then you go for the codec pack, something like this, and you find out T-Lite, right? Mostly, isn't it? And then you're struggling with configuration after installation, right? Yeah, it is so. Why we do that? Well, all of those methods, all of those functions are written in the codec packs, and we literally, with additional configuration, we're saying what will be the quality of the compression. Will we be using more lossless compression than loosely compression in specific cases? Well, all of those things are just mentioned there, and we can mm, we literally can configure that. Yeah. So literally all of those functions, when we look for when we watch movie, so movie information is being just run through the function of the codec all the time. It might happen that visually we can imagine that in a such way. So we have the same original data. For the lossless compression, we compress that, and we can restore data. For lossy compression, we have kind of much better compression, at least it looks like. You can compare PNG and JPG images. You will find out the sizes are significantly different, right? But you cannot restore the original data, let's say from a JPG image. But from the PNG, you can. Okay, a good question for the pictures. What is the original data, right? Original pixel colors. In JPG, they are fake. Oh, focusing. Okay, you didn't know that probably. Okay, have you ever zoomed in a JPG image?
Zoom?
Yeah.
Yeah.
Have you seen that there are vertical lines like a bluish and reddish? Yes. Yes. That's exactly comes from the losing a green color. But picture itself still will be looking normal, kind of. Okay. So we'll be mostly working, guys, on lossless methods. We will be analyzing the Rowland encoding, so-called RLE method. The Huffman trees or Huffman codes, well, some people call it differently, and the Lampel-Z-Welch algorithm, which is used for a long time inside the 7-zip. Well, I would say the Lampel-Z is one of my favorite methods. But the best between them is Huffman trees method. Okay, let's start from the beginning. By the way, you will need to implement all of those methods in Java and upload them as classworks. They're not really complicated, but anyways. So yeah, so here we have some information about that codecs can be very different, and we can have symmetric codecs and asymmetric codecs. Well, literally, the story here is pretty simple. Mostly we use symmetric codecs that approximately allows us to get what time is needed for processing the information. Asymmetric codecs are kind of better. They much better. They compress information better. So we store that in a smaller so-called info volumes. But in the same time, we cannot really make a strict prognosis of the time which is needed. For example, we can show even that it's needed like a 6 minutes, but in reality it's 1 minute, or in a different way, like we show in 1 minute, which is looks like, but in reality it takes, let's say, 6 minutes. So that's about the asymmetric codecs. They're used, but mostly for writing information on drives. For example, CD, DVD, and so on and so on. Well, maybe let's move forward and let's start talking about the RLE. So such method gives the best influence for binary codes. Surely, when you will be using that method, you will be using bytes, so you will be using symbols for storing the data and just working with the data. But its best influence is on binaries. Well, here we have one of methods of such approach, which literally says that we are about to replace repeated symbols or repeated portion of data by mentioning that data plus amount of repetitions. Literally, we can say that we will have a separator, and we have to say that we have to figure out what will be that separator. For example, it could be such symbol. or you can imagine of whatever else symbol. That's totally up to you. Literally, in which cases it's practical to make the compression? Well, when we have more than three symbols in a row, right? Because if you have one, it's not practical to get three symbols afterwards, like a dash one. If you have two symbols, again, it's not practical. Even when you have three symbols, it's not practical. Only if you have more than three, then it's practical. So instead of let's say four symbols, 4 bytes, you will have 3 bytes. Makes sense, right? So it's one of the methods. Sometimes people say that, well, why do we need to not to mention amount if we have one or two symbols? Well, let's mention all of those amounts. That's another approach, but I would recommend you to stick with such method because it's much easier for implementation. Next thing, well, we can think only about portions of zeros, and every one can be described as, for example, a gap or a transformation to some zero or a couple of zeros. That would mean a combination of ones. This method is well, it works as well, but I wouldn't say that it's very famous for just making some small applications. Well, what else? Um, we can have amount of repetitions before the symbol, if you like. But again, I would really recommend you to try to implement the first method because the first method is much easier. Yeah. So that's what I would really recommend you to do. If we would try to, for example, analyze how is this method effective? Well, for example, here you see that we literally have 6D last, so we saved six symbols, right? And here we saved two symbols. So literally, we got the size for 9 bytes less. So is it a compression? Yes, it is the compression. Would you agree?
Yeah.
Okay, so guys, at this time, I would like to ask you to try this method, both compressing and decompressing the text. As the example, you can take the text from presentation, like this one, and you can put that in a textual variable, and you can try to implement it.
First, you want to make Java.
Yeah, sure, in Java, yes. If you will need some ideas how to make that, you can, for example, take a look on files which are written in Python. As you understand, I'm not giving you the codes in Java, right? Or on some purpose, isn't it? Yes. Otherwise, it could be just a copy paste, and that would be enough. But it's not. But it's not the thing which we would like to reach. Right?
Python.
But again, the algorithm, I suppose, is more or less clear. So if you will need that coding, well, I don't really think so. But you can, well, always try firstly on your own. Guys, we're not going through other methods. Firstly, RLE method, and only then we'll talk about other methods. So it's page number 16. of data compression presentation. Okay, and unfortunately, again, we don't have any other students, so we have only you guys connected with the session. Okay, it is what it is. Oh,
Maxim,
hello.
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 How are you?
Oh, fine.
I forgot that you should be today. Please come to drink coffee. Maybe later.
They are working on this.
Uh-huh.
On this. So, they will have a lot of things to do today.
Uh-huh. And you will stay tonight.
Yeah.
Should ask you to go home. Yeah.
Oh, well, this is also, she said that I will get another one, but she will inform me
But
afterwards.
she knows. She knows.
Yeah.
Okay.
So
But I will
she's-
check.
Yeah. Okay.
Okay.
Mhm.
Okay, so we will meet because I have left classes now. My classes
Uh-huh.
I see that anyone exactly. Suprantat, ką daro?
Jo.
Aha.
Tonas labai panašus su tavimi.
Pythonus?
Aha, toks su Java, tai su palyginti.
Mhm.
Mūsų Advent.
Okay.
Sorry?
Advent.
You're done?
I think so, yeah.
You should check.
I will have to check. So I gave them just for an idea Python codes, so they wouldn't copy paste the Java. But it looks
Python
like
is simple. It's
Similar.
similar
Uh-huh.
to Java.
okay. So I didn't have to give you those skills. So you have to think on your own. Then.
Okay. See you next
Okay. Yes. See you. Okay. So go ahead. Show how it works. Yeah. And decoding.
Java is simple. Same Python. This, but you have to do this.
Uh-huh.
It's simple.
Ah, okay, you have it. Mm-hmm. So it's easy. Yeah. Okay then, let's wait for others. But I somehow see that you're kind of looking for all the codes and you're not trying it on your own. Just kind of.
I just stopped basing.
Okay. Okay, let it be so. Is there anyone who finished as well? No, not yet. Okay, okay. Then if you like, you can check the next one, the next method. I wouldn't recommend to copy this one, but I would recommend to think on your own how to make this. Because this is Python specific code.
Yeah.
This is Python specific. Especially this part.
I see. I can play this.
Exactly, yes. Mhm. Okay, so maybe guys, I will describe them for you how that method works, right? In a minute or in a few minutes. Then, because it's really faster, but implementation, I would say, will be really needed in Java. So, what is an interest about the Huffman codes? What you have to do? The first thing you have to collect appearance of each symbol. What does it mean? If you have A, B, C, D, E in your text, you have to find out appearance in percentages. Well, as you understand, 0 is 0%, 1 is 100%. So what does it mean 10%? So each tenth letter is A. Makes sense, right? Okay. Or let's call it 10% of the text is A symbol. So next you have to make the array, and you have to sort the array of these appearances. And you have to combine two last appearances into one element. And again, you have to resort. And you have to do that all the time until the case that you will have only one element in the end, which will have the 100% of appearances. Make sense? Yes? And why we do that? After that, you have to construct the tree of those appearances. Well, in a way, how you combine them. And this is maybe the most complicated. But think on your own. I have a solution, but think on your own how to implement this. Because you know, when you read something on your own, well, it's more interesting for yourself, right? To find out a solution. So here, what you do, you split that in the way how you combine them previously, and you name each of the left path as a 0 and each of the right path as the 1. And literally, you have to combine the paths from the root till the leaf, because on the end leaves you will have letters. And literally, you will collect such paths for all of the leaves. And literally, by that, you will say that each of characters involved in the text will have its own Huffman code. Makes sense, right? And then the story is easy. What you do next? You just go through the text, let's say from left to the right, and you just replace them according to this table. That's it. And if you do that from the left to the right, then decoding works in a similar manner from the left to the right. So if you would like to go from the right to the left, then you would need to name those ways differently. Left will be 1, right will be 0. But since left is 0, right is 1, then here we go again and collect bits from the left to the right. For example, 1. Do we have 1 here? No. 1, 1. Do we have 1, 1? Yes, it's E. So we place E, and the buffer is empty. So we place in the buffer 0. Is there 0? No. 2 zeros. Is there 2 zeros? Yes, it's A. So we place A and we empty the buffer. Make sense? And this is one of the most brilliant methods. I'm not kidding, guys. It's really so. It's a bit complicated to implement, but it is very, very good method. Let's find out what is the compression ratio, right? So initially we have 10 symbols. Let's call it 10 bytes, right? So how many bytes do we have here? Let's compute 1, 2, almost 3 against 10. Is it valuable compression? Yes, definitely. So yeah, so I suppose it will be interesting to make this, right? Because if you will make that, let's call it when you will make that, you can always use such thing in your own applications. For example, compressing data and sending that from your server to your client applications. It will just make the traffic economy, I would say. I suppose you feel a difference. So that's why we talk about this. And people use this all the time. Maybe much more frequently. It's a LAMP-LZ vouch because it's easier to make that. But if you make such method, then things will be great. Right, guys, so I would say stage is yours and you can try to make this. Surely those Python codes, they're Python specific because that method is not great, how I made that, but I just made that without looking anywhere. Actually, I was showing one of students how to make that. So that's how that code was created. That works, but it's not really great.
Ну, практически
Not so.
Okay. And you guys uploaded that, right? In the system? The first one?
No.
But you have to.
Yeah.
Okay. Okay. Don't forget the phone. Ребята, не попробуй. О, можно почти все готово, значит.
Это Python.
Окей, я понял.
Хочу посмотреть, как сделать.
А что вы делаете? Вы что, конвертер пустой взяли?
Нельзя. Это...
Все, я понял, да. Понял. Так, а как у вас было?
Что файл потерялся?
В SRT ищите, не фаунс. В SRT.
Сейчас буду еще создавать.
Подождите, ну, кликните куда-то сюда. Откроем здесь. Щелкнем на треугольничек вот здесь. Не Хорошо, я понял. Так, давайте, такая. Ну, давайте посмотрим, как у вас вообще записан. Да, конечно. Давайте смотреть код, который у вас есть. Что это такое? Вы с файлом читаете, я понял, хорошо. Ну, давайте компресс текст смотреть. Ага, молодец, давайте в код смотреть. Так, аккаунт 1. Если человек другой, тогда... ну так смотрите, у вас же, вы же что делаете? Если у вас больше одного символа такого, тогда вы сразу ставите там 2 и 3 тоже. А вам надо только если больше 3 так делать. Да. Ну я не знаю, это вы же написали код. Давайте посмотрим. Ну, вам надо сделать так, чтобы не открылся код. Смотрите, противный случай, да? Сделаем противный случай. Давайте сделаем блок кода. Молодец. Теперь смотрите, ну, если вам не надо делать ничего, может быть, добавим эту же букву в конверсионный текст? Ну, вместо решетки добавим ту букву, которую мы сейчас видим. Она будет убраться. Ну, только не решеточку, а input поедет сюда. Input, да? Или почему? Или char S плюс. Или char S.
А там точно нужно?
Да, нужна, конечно. Только, по-моему, оно вот так было. Вот ставим и ставим букву И здесь. И пробуем запустить. Да, что-то не появилось. Нет, в принципе, почти все так, только какие-то символы лишние. Так, если мы встретили символ, который уже у нас есть, то мы увеличиваем колор. Если у нас если другой, тогда нам необходимо записать информацию про предыдущий символ и сказать, что мы нашли новый. Разве не так? А почему вы делаете input char и input char -1? Ну, стоп. Так. Не, ну тогда надо -1 здесь ставить. Не и, но и -1. Да. Ну, конечно, это получше, но все равно не очень. Append count. Ну, зачем вы дополнительно append count ставите? Это не убираем. Ну, единственное, что у нас еще буква А появилась. Угу. А знаете почему? Потому что, скорее всего, вот это лишнее. Компресс, наверное, вот это. Ну, нет. Давайте берем и запустим сейчас. Да зачем? Нет, просто запускайте. Да нет, но на самом деле это лучше. А знаете почему? Потому что кое-чего не хватает. Вам бы еще вот такую вот штучку поставить вот здесь. Вот, видите, у вас сразу две решетки, там наполнились буковки. Да? Остались только места, где у вас не нужно компрессию делать. Вот подумайте, что вы еще можете сделать. Ну, если их больше 3, тогда мы делаем компрессию. Если меньше, то что мы делаем? Столько, сколько мы нашли, да? А мы даем только одну штуку, если вместо того, что мы нашли. Значит, что вас это делается? Если мы нашли один символ, если мы нашли два символа, если мы нашли три символа. Да? А у нас только один идет. Вот поменяйте. Да, именно вот в этом месте, конечно. Okay, Louis, also how's your progress?
That's what I'm from Barcelona, but I'm still trying to figure out everything by myself.
Progress.
Similar problems, crossovers.
I just assume, no. What do we have here? We are finishing something and we try to do the same, right? And the brackets are closed. Isn't it?
Yeah.
So it might happen, this should be erased or this two lines should be erased. Right? I don't know by the logic of your code which ones.
I think these I don't know.
and one, in this case, one of brackets is missing. The last one. Erase this one and put instead of that the bracket, the curly bracket. What are you doing? You erased another one. Why? Instead of this text, put the bracket.
Instead of this.
Yes.
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 Yeah. Okay.
Yeah. Now that's worse. If you compile it. Okay, here you have some I, but what is the I here? Where's the I? It works only in this form. That's it. I don't know. Do you have what that I will be putting in the end? It will be the last index of input.
Can use another variable.
Oh, wait a bit. You have the same code as we have there, right? Okay, so just look what is going on there and just copy that. Because it's the same, it's totally the same stuff. Ну, что мы тут делаем? Нехорошо, очень нехорошо.
Но тут хорошо.
Но это неправильно. Это неправильно.
Так это
Да, обязательно. Сказать? Если один, то один символ, если два, то два символа, если три, то три символа. If count равен одному, то один символ. If count равен двум, то два раза. If count равен трем, значит три раза. Ну, почти только вокализ забыли. Равен не приравнивается, а равен. Вот проверку делаем. Два знака равно должно быть. Да, правильно. И то же самое, если три.
так можно.
Вот так можно, да. Копируем вот эти две строчки и вставляем чуть ниже. Вот эти, да. Ну, без Нет, что вы делаете? Ctrl-Z. Ctrl-Z нажимаем. Немножко. Вот, берем вот эти две строчки, без скобки. Копируем. И сюда вставляем. Если тогда 3, то еще строчку добавляем. Ну, еще 7. Ну, теперь оно должно работать. Ну, теперь это правильно. Да, теперь надо все раскодировать. То есть у вас есть теперь вот этот текст, а вам нужно оригинал получить. Definitely take a look at the solution for your code as well.
I'm still figuring out a couple of things myself.
Oh, okay, that would be much better than looking just for a solution. How's the progress, guys?
I don't know.
Okay.
So
Oh, you're copying, right? And how's your progress? So Python to Java. Well, sorry, but it's not what you have to do. You have to try it all. I expect this was your response. Maybe you can look and see a code.
Sometimes even the answers to decompression.
But you
How did we get compression? Show me the code of compression.
super, Fajnie ze strukturą to ma być bez systemu, który jest szalce. Wyszli teraz. Całe szkoda Polsce to są
You wonder why you couldn't do it. Yes, because it's not practical to compress when you have to. So you have to fulfill this with the piece of country So you can print off these symbols. And you could do that more elegant. More elegant. More elegant code. Okay, I will show it, right?
Yeah.
Then what? You see, it's easier. It's more cool, right? Then this kind, the new one has one time you found it. If it's not, then you should do anything now. You see, function becomes 0, 1. Oh no, okay, afterwards you increase that. Okay, makes sense. So let's see what we have. How many we have here? 9, so we have 12. So yes, so it's not a surprise what we have. It's correct. Because we have 12 these.
We will do.
This.
And
This
then
is
go
in
ahead
the
and
middle,
this.
right? So 12. So this is fine.
Yeah.
But only when you have 3. Because here we have more than 3. Because if it's 3, it's a flat. And so you will have 1, 2, 1, 2, that's it. 4, 3, 7, 1, 2, 3.
Czyli to było
A ty gubiąc.
The previous character is the same. So after this, the previous character will be the same. So okay, let's now we put that 0, then we say okay to become this one. Then we here again.
A ty nagadam pisał, że ty podrył. A ty ty?
2, 4, 6.
Gdzie? Mamy kompresję. A tai reprezentuje mano kaip pavyzdys, padaujant iš šito skaičiaus šito DT.
Mum reikia sukompresinti, tada iškompresinti.
Tu supranti? Aš suprantu, aš apie tą pasiūlymą sakau. Sprendimą. Sabe que tem que ter conforto.
I would say you have to print out how many times did you run this line. Maybe you can just put some output here. Yeah. With the uppercases. For example, the previous character. Yeah. Output 0.3. Okay, with the line and previous character. Yes. Okay, maybe the counter as well can be printed out after the space. Prefer plus empty symbol and counter. Yeah, well, yes, space. Plus counter. Let's run it. 1, 2, 3. Then you have here. Now this one is just a bit confusing. But what the previous character is not the 0. Oh, it's the 0. Okay, that's not the 0. So so it looks like that. We have the counter printed. Like cruising song.
The pins count from 0.
Okay, yes. Yes, because you put the first one here. That's what it's So you're not printing out this case. I don't know. We have to think about this. I'm not sure this kind of how it happened.
Let's go with it.
Так, ну и вот что у вас.
Да спался долго.
Что у нас тут такое? Скажите мне.
Ничего, я только нажал чуть долго пошел.
Ну, я смотрю, вы
Ладно.
вчера рады были нажатию кнопки.
Без.
Весело, да, это тоже такое.
Oh, Complex house.
Как увлекаться?
Leave that is the leave. With the baby.
Ну, конечно, знаешь,
If it's a local, I guess you get the.
еще попался.
How's your nose? Is there anything you can do with it? Ah, yeah, the cool
Big compressor.
So you made that, right? Mm-hmm.
To the sausage.
Okay, guys, so looks like yes, we have to take the lunch break. Okay, so after the lunch break, we will continue.
You are currently the only person in this conference. You are currently the only person in this conference.